Hi, my name is Marit Bentvelzen, and in this video I will present our paper on how instructional data physicalization fosters reflection in personal informatics. So our lives are characterized by an increasing amount of data, and personal informatics, meaning the practice of gathering data about our health, well-being, and activity, has become a prominent feature of everyday technologies. One of the remaining challenges, though, is to design technologies that enable or encourage users to reflect on their data. Many studies in HCI explored how we can design technology for reflection, and in one of our previous studies, we created an overview of the strategies that were used in both HCI research as well as commercial smartphone applications for reflection. This resulted in a taxonomy of 11 design resources and 74 design patterns that can be used to foster reflection. One of these design patterns is the use of tangible data representations, also called data physicalization. Data physicalization is an established topic in HCI. Several studies explored how the use of physical data representations supports users in exploring and reflecting on their personal data. For instance, Loop is a tangible situated display that visualizes users' fitness tracker data by moving the position of the rings. Sweat atoms, on the other hand, are 3D printed physical representations of fitness tracker data. And in a study by Toet et al., participants constructed their own data representations of self-selected metrics. Past research shows clear potential for physicalization, fostering reflection, yet the variety of results and the levels of involvement with the artifacts show a need to understand this design space more systematically. Therefore, we investigate how data physicalization can benefit data exploration and reflection in personal informatics. We conducted a between subjects mixed method controlled user study using 3 conditions and a total of 60 participants. We were interested in the consequences of using either a digital data visualization or a tangible data representation, and also if introducing a more instructional approach of building a physical representation would affect how users explored their data. In the study, we wanted to be able to compare between the 3 conditions, and therefore participants needed to interact with the same type of personal data. Now, this personal data could have been anything from screen time to heart rate variability. In the end, we decided to use blood pressure as this metric has some benefits. It's a metric related to health and well-being, which is in line with the majority of work in personal informatics. It can be measured with an off-the-shelf consumer device. A single measurement offers a reliable value, and it has the same ranges for each participant, regardless of age and sex. So what did the study look like? It took participants approximately 30 minutes to complete the study. We started with an introduction, followed by the blood pressure measurement. While the data was being uploaded, participants filled out the demographic survey. Once the data was uploaded, participants then interacted with their data in one of the 3 conditions, followed by a survey and an exit interview. We evaluated the 3 conditions using 3 measures. First of all, we wanted to evaluate if the conditions had an effect on reflection. We used a technology-supported reflection inventory to measure this. This validated scale consists of 3 subscales: insight, exploration, and comparison. Next to this, we evaluated user engagement using the short version of the user engagement scale. This scale consists of 4 subscales, being focused attention, perceived usability, aesthetic appeal, and reward factor. In addition to this, we measured the time a participant spent engaging with their data in seconds. To measure participants' blood pressure, we used the Withings BPN Connect. This is an upper arm monitor integrated in a cuff that inflates automatically with the press of a button. This particular device is not intended to be used as a medical device in the doctor's office, but enables users to track their blood pressure at home. It is designed to be part of one's personal informatics device ecology, and therefore suitable for this study. The measurement consists of 2 values, a systolic pressure, which is when the heart beats, and a diastolic pressure, which is between the heartbeats, and it's expressed in millimeters mercury. In each of the 3 conditions, our participants explored 4 values, their personal measurement and the optimal values being 120/80. We randomly assigned participants to one of the 3 conditions. As a baseline conditions, we used the Withings HealthMate smartphone application, which is the accompanying app for the BPN Connect monitor, and therefore we considered this to be a strong baseline. For the other two conditions, we had participants build a tangible data representation using Lego bricks. In the instructive data physicalization condition, participants received pre-counted bricks from a custom-made brick dispenser. The dispenser consists of 4 towers related to the 4 values of the measurement that each contain 20 Lego bricks. Each brick represents a value of 10, so a measurement of 120/80 would be represented with 12 bricks in one color and 8 bricks in another color. Participants were instructed in this condition to build a tower for each color. Finally, in the third condition, we gave participants a wooden tray with 4 different colors of Lego bricks, with 20 bricks per color. In this condition, we did not provide any instructions. Instead, we asked participants to build a visualization of their measurement and the optimal blood pressure values. We gave one hint that it might be easy to have one brick represent a value of 10, but they were free to also decide differently. So, what were our findings? In general, participants in the baseline condition struggled more with the complexity of the metric. Some expected a single value, and participants often expressed the need for the application to provide additional information for interpreting the numbers beyond just stating the desired values. Participants that interacted with the bricks did not express this confusion, but instead mentioned that constructing their data was a calming activity that helped them focus and think about the measurement. However, the ANOVAs of the TSRI show no significant difference between the 3 conditions in reflection, nor the subskills insight and exploration. There was, however, a significant difference for the comparison subskill. Participants in the instructional condition found it easier to compare their data, which was also expressed in the exit interviews. This benefit in comparison was not just due to the physical representations, as participants in the free-form condition did not find it easier to compare their data. When we look at some of the final builds, this may have been due to the sort of representation that participants built. The 4 towers look a bit like bar charts, and the difference in height makes it very easy to compare the 4 values. Some of the participants in the free-form condition made visualizations like the scatter plot, or some spatial designs with mixed colors, which could make it harder to compare the values. In general, participants in the free-form condition struggled more with their task. Some participants found the task too complex, and others expressed that having to think about how to physically build a visualization actually disconnected them from their data. It made them focus solely on the visualization task, and it drew attention away from possibilities for reflection. This was also reflected in the engagement time. Participants in the free-form condition needed more time building their representation. There was even one participant that took 22 minutes, while on average participants spent 6 minutes on the task in this condition. This might have been a reason for the significant difference between the baseline and the free-form condition for perceived usability. On the other hand, both physicalization conditions showed a significant difference in focused attention, implying that a physical data representation helps users to take their time and focus on the data. The results show that physicalization of data does not automatically lead to higher levels of reflection, and it indicates that designing physicalizations involves balancing between offering freedom on the one hand and providing structure and guidance on the other. However, we also recognize that there are some limitations to our work. First of all, the choice of using blood pressure. Blood pressure is a complex concept, and future studies should investigate if the use of less abstract metrics, as well as self-selected data, affects the perceived engagement and reflection of participants. Second, we used a snapshot of data in this study, and it remains a question if the use of data physicalizations could also benefit users over a longer period of time. Finally, our study took place in a controlled environment with a single metric. In reality, users of personal informatics systems track a wider variety of metrics that they try to understand and reflect upon. The challenge of using physicalizations in this context is to guide this process to avoid the user getting overwhelmed by all the possibilities of designing physicalizations. We hope that our work will inspire future studies into engaging users in personal data journeys with tangible representations. Thank you.